Good afternoon, everybody. Welcome back to lecture number 10. Last time we talked about the frequency and voltage control, and similar to the homework, we have a closed loop feedback that controls the frequency of the synchronous generator, feeding the control result back to the fossil fuel input, the steam, till the steam become less or become more. For the voltage sensor, for the voltage values, we can control it using the AVR, and the feedback goes where? To the excitation system. So always for every synchronous generator, you have to know that you have two ways to control. You control the voltage using the exciter, you control the frequency using the input power. So in every example, we will see examples today, when we talk about the input power is maintained, it means delta P is 0. When we see we increase the input power by 20%, it means this becomes 20%. Delta P is 20% of the measured value. When we say the excitation voltage is increased by 20%, it means this excitation voltage is increased by 20%. So you have two ways to control the synchronous generator. Also, last time we talked about, it turned out that if you increase the generator power, you tend to have a drop in the frequency. If you increase for the same curve, for case 1, for example, if you increase the generation or the generated power, your frequency should drop by an amount called delta F. Thus, you need to compensate it by adding this delta P control signal to maintain the frequency constant. If you look at the Saudi electricity company standards, the frequency should be maintained between 60.2 to 50.8. This is the preferred, and the allowed region is 60.5 to 59.5. If we reach 61, we're in a disaster mode. Okay? And how much the voltage? 5%, plus or minus. So if you control the frequency and the voltage by 5%, you put these numbers, you are in a safe operation mode. Okay? Let's look at what you don't like, the phasor diagrams. Let's look at this phasor diagram. Okay, so let's say we have VT1. For VT1, I have I1. Is it leading or lagging? This is lagging. This is the angle of the power factor. And it's of course lagging because current lags the terminal voltage. From the example, the previous example, let's find J XS I1. So J, it means 90 degrees, scale it with XS, which is this vector, you see it? So let me move it to the tip of VT1. So this is J XS IA1. IA1, armature current 1, that corresponds to the terminal voltage. Then what should I do? I do the vector calculation. Okay? I do the vector calculation to get EF1, which turns out to be EF1 is this vector, which corresponds to the equation EF1 equal VT1 plus J XS IA1. This is, we ignore our armature. Okay? Let's continue. Now, for some reason, what happened here, the bus voltage decreases because the demand has increased. We're pulling more current into the system. The armature current I1 increased to I2. So I2 is the same, we have the same power factor, but the magnitude is what? Is a bit more. So this is IA2. Put the same thing on the tip. If I keep EF constant, if I keep EF fixed, I cannot reach the JXSI2. For some reason, I have to increase the field because this is longer. If I maintain IF constant on a circle, I cannot reach that tip. Clear? So I have to, if I maintain EF, VT has to decrease in order for me to reach the EF constant operation, the constant field operation. You cannot have them both. You cannot have them both. You cannot have EF constant and armature current increases. Conservation of misery. You cannot have them both. You always have to sacrifice one of the elements if the magnitude of IA increases. So what will happen is, which one is more important to maintain? The terminal voltage of the generator or the field excitation voltage? Which one? The terminal voltage. Because customers pay to get constant voltage. So terminal voltage of the generator is always maintained. As a cost, what's the cost? You have to increase the excitation voltage to a lengthier than the previous one. And this is the job of the exciter. Get it? Clear? So in the exam, we'll ask you questions like the ones in the red. Describe using phasor diagram how the FR system maintains the terminal voltage at inductive load increase. So if we increase IA2, we either have to reduce VT2 to get constant EF2, or we have to maintain VT1, we have to get another EF3 longer than EF2 and EF1. Cannot have them both in life, okay? So this is how frequency and voltage control of synchronous generator. Hopefully now you know how to control the synchronous generator. Most of the problems we do in this course, we mess around with the excitation voltage. Okay? This is much more difficult. This is much more difficult to have a numerical problem because we have to look at the transient simulations. And one of the software that they use to assess the frequency of the system, we call it EMT, electromagnetic transients. The software is RSCAT, RTDS, real-time digital simulator, that uses RSCAT. So it's real-time systems CAD. We have it here in KFUPN. Maybe one day we'll have a look into it. And I forgot to mention, do you guys want to have a field trip?
Yes, for the lab.
You guys are taking the lab, but who's not taking the lab? So those who are not taking the lab, do you want to join the lab in their field trip?
Yes.
Yes. Yes.
Okay, so we'll make it mandatory. So we'll cancel the lecture of the field trip the same day, and the attendance will be taken in the plant, okay?
نروح بلاد.
I think plant. دكتور محمود قصاص يرتب لهم. He knows where to look at. So those who are not taking the lab, you're free to join, or you have to join, okay? You have to join.
For other classes, so
What other classes?
like maybe after this class I have other class. Or it will be in the
take
10th class or
Who's teaching?
لا ويعتمد على اليوم بس يعني.
We can talk to them or write them letter or please. تمشي الأمور إن شاء الله.
When is the field trip?
I don't know. The lab team.
كل يوم اللاب.
It's one of the.
قال يوم الخميس.
It's one of the Thursdays.
الخميس.
It's one of the Thursdays.
اوكي.
ممكن بعد رمضان. I don't know.
زين.
Yeah, these things you have to make your free absences there.
لا كويس زين.
We can talk to the instructor. That's okay. So enough talking about synchronous generator. Let's talk a little bit more about synchronous motor. Do you remember I told you in the synchronous generator the alignment between the poles is what determines the delta?
Yes.
So one of the problems of synchronous motors is they are not inherently self-starting. They do not start by themselves. You have to either synchronize them manually at the same speed or use some of the techniques. Induction machines, the moment you connect them to the plug, they start spinning. DC machines, the same. But for synchronous machines or synchronous motors, you cannot. You have to do some techniques. So why this is happening? If we look at the stator poles, north and south, you can have 2, you can have 4. 4 motors, if you have more than 8 poles, something is wrong with your machine because it's going to be too big. And we tend to have small synchronous motors. Why there is an arrow indicating that the poles are moving at 3600 RPM? This is one of my favorite questions in the exam. So you have to watch YouTube. Can the poles rotate mechanically?
No.
No. They're fixed.
So can the stator rotate?
No.
So what is rotating?
The magnetic field.
No, it says the arrow هنا في الرسمة يحط لك 3600 على الستيتر poles.
magnetic field generator.
But why it rotates? Because this is a uniform rotating magnetic field. This is the technical answer, uniform RMF. A uniform RMF would rotate at 3600 RPM. However, the rotor at standstill, it has uniform DC excited field. If I'm not spinning it enough, this will be at speed 0, this will be at speed 3600 RPM because it's at 60 Hertz. In order for me to align the south and the north with the torque angle and synchronize both of them, if I start from 10 Hertz converted to RPM, how much? 120 times 10 divided, let's say 2 poles, 600 RPM. If for some reason I'm spinning the rotor at 600 RPM, so every time the S comes closer to the north, we will have a torque that's pulling the S toward the north. Okay? However, at another instant of time, the moment that the south becomes the north and north becomes the south, because it's faster, 3600 is faster than 600 RPM, we will have a counter torque compared to the previous case. I'm spinning the rotor slowly, I just start spinning it at 600 RPM by any means. The fact that the north and the south pole rotating and they change locations faster than the rotor would tell me that the torque would change its direction because one is attracting, north is attracting the south, but here the south is repulsing the other south. So one time the torque kicking in, the other out. So what's going to happen is that the rotor would just be moving or vibrating a little bit. It will not be rotating full circle because of the fact that the uniform RMF changes its position. Clear?
Yes.
Do I need to elaborate more or that's enough? Clear, right? So how to start it? There is 2 methods, and you know, quiz 2 we may see this question, or the fake quiz. When do you want to have the fake quiz? Thursday, okay? Short.
This Thursday.
Yeah. You have to. The rule of thumb for every course, every 2 weeks there is an official quiz, because 15 divided by 2 is how much? 6 or 7. Some weeks we will cancel them. So let's have the fake quiz this Thursday. It's going to be short, I'm not going to waste the whole lecture. Okay? Thursday we'll have the fake quiz. For those who missed the quiz, this is your quiz. For those who are doing it, it will be counted at the end. Okay? I'm not going to do like 360. We'll make it useful. It will push your grade higher. Okay? I promise. To be fair. If you don't want to do it, don't do it. So one of the two methods is either starting at reduced supply frequency. You make this 3600 RPM, 600 RPM, 10 hertz. If you make it 10 hertz, then the rotor will catch up and it will be synchronized and then gradually increasing the frequency. So this job is achieved using variable speed drive, VSDs, power electronics. You remember VSD in the power electronics? You start at a low frequency. Which one? The rotor or the stator? The stator. You start instead of 50 or 60 hertz, you start at 10 and increase it gradually so that the rotor would catch up. The other method is starting the synchronous machine as an induction machine. And this is achieved by some sort of supplemental mechanical components. And what I mean is, you remember the squirrel cage, which is bars made of aluminum with end rings that are short-circuited. You put it in, and you put a rotor in a cage. You put the excited rotor of a synchronous machine in a cage. If you put it in a cage, the moment the rotor starts spinning, it will have an end ring where an induced torque will be stronger than this torque that we experience between the exciter and the stator field. There will be an additional torque that would counteract these two torques that spins. Clear? So basically you're putting an induction machine for the very small frequencies until we reach the synchronous speed. The beautiful thing is at synchronous speed, what is the slip? So slip at in sync equal to 0. It means the bar current in the squirrel cage will be DC. So if the current is DC, it will not induce torque. So I don't care about it. This is the more common method. For this purpose, an additional winding which resembles the cage of an induction motor is mounted on the rotor, on top of it. The cage type winding is known as the damper winding and is shown here. Damper winding. Which one is more expensive? You buy power electronics or you buy a squirrel cage made of aluminum? Now what are the downsides? Is it will add weight to your motor. It will add weight to the motor. Also there might be some minor losses for at slip 0. Small current.
وش المشكلة بالويت؟
ويت يعني
يكون فيكس بمكان معين للموتور.
No, it will draw more current to carry the same to rotate the same rotor. If it's heavier, the inertia is higher. The stator magnet has to put more work. Nothing is free. So that's one of the downsides, is you add more weight to it. But sometimes for EVs or this is not a problem. Let me tell you one thing. Electric motors are mature enough. It means the progress in them is very, very slow. So if you're planning to do research, like what I did, in machines, it is very difficult to make an achievement. Nikola Tesla left nothing for us. Because there is nothing you can do. There is really nothing you can do. The only thing you do right now is to come up with better magnets or come up with a new material that's better than steel. You mix composition, material science. So as an EE, there's much, we did our job. It's now the material science to discover the magnets. It's not only that, most of the innovation comes in the drives now. Most of the innovation comes in the drive, and as you can see, this is the frequency converter. It converts the frequency from 60 hertz to 10 hertz in order for us to achieve or minimize this counter torque that we see.
دكتور بس إذا أضفنا السكورل كيج
هل بيبقى synchronous ولا بيكون asynchronous؟
No, it will once it reach. Okay, what was the induction machine? If you don't have an excited rotor, what will happen? The moment you reach synchronous speed, the current will be DC, so there will be no torque, so it will slow down. But here you have an excited rotor inside, تحت الcage. For this excited rotor would still have this torque T that would maintain the synchronous speed, so it will stay at synchronous speed. The impact of the cage is temporary, only during the startup. So it's your choice. You wanna start it, lose some weight, and then during synchronous speed this will be useless. Remember the equation? The frequency of the bar current. Frequency of the bar is the slip times F supply. So it will be 0 hertz. That's why it's DC. There might be some current. So you might have a minor losses. But this bar that is excited using DC would still rotate at synchronous. Get it? Can you please, anybody check? We need a cameraman.
Yes, so
Okay.
So this is one of my favorite questions in the exam. It will come in the fake quiz. خلاص?
what's the question? Sir?
This is the question. Starting with 1, 2. اللي ما يحبون الحفظ, you have, now it's maybe time to memorize. Who's the example I told you? You can tell them.
وش أي example؟
That I showed you in the office. Who was memorizing every number.
حق أرامكو شو اسمه أيمن
أي ما تعرف رئيس أرامكو؟
نسيت اسمه.
أمين الناصر.
Mr. Amin al-Nasir. I attended a dinner one time when I was with Aramco. It's okay. When I was with Aramco, he had a dinner for young engineers who joined the company. He's a very smart CEO. And one of the PDPs is like the first 3 years of employment, asked him how to be successful. What can we do? When he said to be successful is you have to read every document that is in your facility. So the more you read, the more you become familiarized about the sizes, the data in your
Standards.
the standards and everything. So you have to memorize, but you have to memorize the smart way. And during the interview, how many numbers? Every 3-4 sentences, there is 1 or 2 or 3 information. So you have to memorize. حفظ جيد. To some extent, like if you understand these concepts, you can memorize easier. Okay? And also read the documents. You have to read. So example 4 and example 5 are much easier. They are way easier than example 3. So I'm going to walk over them quickly without solving them. They're easy to explain. They're very close to 360. 3-phase, 5 kVA. What is 5? Wrong. Wrong.
Reactive.
Wrong.
Right.
Wrong. It's rated.
Right.
You have to add the word rated. It's rated apparent power. What is 208?
Rated.
Rated what?
Line to line.
Line to line voltage. 4 pole, 60 hertz, star or Y connected synchronous machine. We ignore RA, synchronous reactance of 8 ohms per phase. Is this in per unit? No, it's a regular calculation. At rated terminal voltage, it means at 208. The machine operates as a generator in parallel with another machine of 3-phase, check, same frequency, same voltage, probably same phase sequence and phase. So we satisfy the 4 conditions that most of you didn't know in the quiz. And the solution is posted, okay? The solution is posted. And yes, generator B was leading. Find the excitation voltage and the power angle when the machine is delivering rated kVA, it means rated 5 kVA at 0.8 power factor lagging. Draw phasor diagrams for this condition. To solve this problem, we have to draw the phase equivalent circuit. which implies that we have an inductor, we have our E. So here we have Vt. What is Vt? This is a phase quantity, so it will be 208 over square root of 3, which is 120 volts. Ia, this is a generator or motor? Generator, we're getting to the terminal. And then we have EF. So, at rated current, Ia is what? Power, 5K, over phase voltage, 3 times phase voltage, 120, times the power factor, wrong. Because this is S, we leave the power factor. If it was P, we add the power factor. Get it?
Yes.
Why? Because if you multiply to get P, it's 5 times the power factor, so you multiply by the power factor, you divide by the power factor. Don't, the formula is like that. S equal 3 V phase I phase, or P equal 3 V phase I phase, power factor. Clear? 3/6.
Yes.
The most important course in the junior. Let's continue. Once you calculate the I, it's time to calculate the angle, and it's lagging, so I has to be negative, and the angle is clearly shift cosine minus shift cosine 0.8, which is 36.9. Add, do the KVL, EF equal voltage rise, Vt plus J XS Ia. If you substitute, you get 206.9 at an angle of 25.5, and this is the torque angle, and it is positive. So it means we are at generator mode. So this is, you can solve it with your knowledge in 360. Clear? This is the phasor diagram, Vt, Ia, JIAXS. This is your F, delta is positive, check we're at the generator mode. Okay? Now, what is happening in part B, if the field excitation current is increased by 20% without changing the input power, find the stator current, power factor, reactive power supplied the machine. So here is one information. If I increase the field current by 20%, what will happen to the excitation voltage?
Drop.
No.
Increase.
No. Go back to this curve. Let's go back to this curve. One of the early curves that I put here. If I increase IF, where do we operate? Do we operate in the saturation or in the linear? Linear, high linear, just before the knee. So if I increase this by 20%, what will happen to EF?
Increases.
Increases also by 20% from the curve. You understand now? If I increase the field by 20%, I increase the excitation voltage by 20%, if and only if I'm at the linear region. If I'm at the saturated region, this is false. And no one will operate the machine in the saturated region. So, if I give you this in the question in example 4, you should really understand that if I increase the field, you should write it actually in the exam. If I increase the field by 20%, since I'm in the linear region, the excitation voltage will increase by 20%. Okay? So, what will happen here is the 206.9 multiplied by 1.2 to increase it by 20%. So here, how to solve it? What is this equation? This is the equation of the power, the real power. You remember it? E times Vt over Xs sine delta. If I'm having the two powers the same, P and P prime, so where P is for part A, P prime is for part B, I can equate those two numbers, cancel Vt, and I can write this equation. So I can actually calculate the new delta if EF and EF prime are 1.2. So sine delta prime is sine 25 over 1.2. By calculation, your torque angle would drop by 4 degrees. Why it would drop by 4 degrees? Because now I increase the excitation voltage. If I increase the excitation voltage, the excitation voltage, what will happen is actually the current will be 17.86 compared to the current that was 13. So the current will increase. If you draw similar argument what I made here to maintain VT, EF is increased, IA will increase. Similar to the argument that I made. And the torque angle will decrease. So the torque angle now is 21 degrees. This is trigonometry. We're equating the two powers. We increase the field by 20%. So now with the new EF, with the 1.2 times the part A at an angle of 21, this is VT, this is JXS, you get the new value of 17.86, and the power factor is cosine of VT 0 minus 51, so it will be 51.5. So to be cosine 51.5. Always the angle of the power factor is the angle of the terminal voltage minus the angle of the terminal current. The terminal current is the armature current. Clear? So this is how to solve this part, and then you can calculate the reactive power, which is 3 VT IA sine, or you can use the big equation that has cosine delta. There is one equation before that has similar to this equation, but has VT EF XS sine cosine square minus VT square over XS. There's one equation that I wrote before. You can use it, but I prefer to use this equation because it's simpler, easier to remember. 3 VT IA sine delta. So the reactive power is positive. So we're still at the reactive, lagging power factor. If you use this equation, the one I told you, you still get the same Q. The last part of this question is, with the field current in A, the prime mover now is increased. So we get the same EF. So in part C, we maintain the EF, we increase the real power. What will change? Of course, delta has to change. So here we, from part A, part B, part C, in part C, so here EF prime equal 1.2 EF. Here, with the field current in A, it means EF in A. So here we have EF, not EF prime. Prime mover power is slowly increased. What is the steady state stability limit? You remember stability limit? It gives me one information.
Delta is 90.
Delta is 90 degrees. What are the corresponding values of the armature current, power factor, reactive power at this maximum power condition? To solve this problem, you have to calculate the power max. Power max is a 3 EF VT. EF from part A, you have excess is 9.32 kilowatt. You have to get a new IA, and here you substitute delta with what? With delta equal 90. Why? Because we are at the maximum power. Clear?
Yes.
We're at the maximum power. Why your text?
Double text again.
Okay. Yeah, it's up to you. Okay. So this is 90, this is 0. Then you should get IF. IA. What do we notice at the new IA? It's 29.9. In part B, it was 17.86. So that's almost twice part B or part A. So at maximum power, we draw so much current, almost twice the rated current. Is this good or bad? It's really bad. And what is the angle of the power factor? Only 30 degrees. So the power factor is dropped to 0.865 and it became leading. Why? Because we have cosine of, what's the angle of terminal voltage? 0 minus. What's the angle of the current? 31.5. So the current is leading the voltage, so this is leading. So this is the operating condition at the maximum power transfer. What is the reactive power? It's the same equation. 3 VTIA sine of
90.
wrong, minus 30. So to get the Q is 3 VTIT sine of
Minus 30.
minus 30. And to be accurate, this shouldn't be cosine 30. This should be cosine of minus 30.1. To know it's leading. This is leading. Reactive power for leading is what? Negative. Like the shunt capacitor. Clear? It supplies VARs to the system. So what do we notice? At the maximum power transfer, the current is so high, we're supplying VARs to the system, and the power factor is
No.
drop to leading. So next time we'll go over the example number 5. I think example number 4 is a reasonable question to be asked in the exam. I think it's better than problem 3. So keep that in mind when you make your studies, okay? This is a horrible example because you have to, the only way to solve it is you have to do phasor diagrams. But this example is more interesting. Okay?
Yes.
كم سؤال يكون الميجر؟
I don't know. Rule of thumb when I write my major exams is we look at the material. And I make like one problem conceptual, that's 20%. And I make like 3 problems. So that's a total of 3 or 4 big problems. Each problem is 20 to 30 minutes. That's 2-hour exam. But if it's 1.5 hours, it will be 3 problems. We'll see. We'll see. You want a simulating problem in the exam?
No.
Why you don't like it? So I have a theory. I know why you don't like this simulating. Because you really wanna, you really don't want to get the whole picture at the beginning. Many of you want to do every code, every line they want to understand. Just try to run it, see how it goes. Okay? As a matter of fact, when I developed the homework problem, I took it from one of the examples of simulating. I modified it a little bit, so you can read the documentation of a similar library. And also many of you don't want to deal with the software, but in real life you have to deal with it. As a matter of fact, one of the deliverables of, let's say ABB is doing project for Saudi Electricity Company, one of the deliverables of every product, a demo on Simulink. It's used, Simulink that works. So that before we make the changes in the field, we make the changes where? In their model, in the simulation. Then if it's approved, you go and make it in the field. So time is up, we'll see you Tuesday.